All right, everyone, let's go ahead and get started. My name is Sharon White, and I'm the Marketing Manager for BLT. So welcome to today's webinar, Closing Timing Using Intelligent Design Runs, which is a spotlight on the new AMD tool feature. Before we get started, I just want to take a few minutes to introduce BLT, our speaker, and to go over some housekeeping. To get started, if you have questions, please put them in the chat panel. We will get to them during the Q&A at the end. Today's webinar is being recorded, and I will send that recording out once it's ready. There are no books or slides with today's talk. So now let me introduce to you BLT. BLT has been in the engineering design services business for almost 35 years. Our headquarters are in Maryland, and we also have a design office in Melbourne, Florida. We design chips, boards, software, and complete systems for commercial, aerospace and defense, and intelligence clients. And some of our notable designs include the prototypes for HDTV and satellite radio, and our work on the Mars rover. Our designs are in space, undersea, and everywhere in between. And we've been teaching AMD training for over 25 years. We're also an AMD Premier Partner, AMD coaching provider, and an authorized training provider. We are a complete AMD solutions provider. Our training is by engineers and for engineers, and we bring our decades of real-world experience to the classroom. If you're interested in other training and events from BLT, be sure to follow us on LinkedIn, Facebook, Instagram, and X. I post all of the upcoming events there, so you'll hear about them first if you are following our socials. Today's webinar is being led by Ellie Rosen. Ellie is an engineering manager at BLT, primarily focusing on adaptive SoC, RF-SoC, and MP-SoC designs for both commercial and defense applications, and is one of our resident embedded experts. Ellie has spent many years managing AMD Xilinx-based FPGA projects, and before coming into this role, he spent countless hours designing, integrating, and debugging radar systems, underwater sensors, and cryptographic ASICs. ASICs. I can speak today, I promise. He's also a general tech enthusiast that enjoys playing with SDRs and home automation on the weekends. Before we get started, I'm going to go ahead and throw some links into the chat panel for you for some of our upcoming events. We have a webinar and a workshop coming in February. So our webinars are an hour long. Our workshops are 4 hours long. I will put our February events into the chat panel for you, and also our course calendar if you're interested in checking that out and seeing what we have to offer. So I will step back now and turn it over to Ellie.
Thank you, Sharon, for that. I appreciate the introduction. Like Sharon said, today we're going to go over the intelligent design runs, and that is a new feature within Vivado of the last year. It was first introduced in Vivado 2023.1, and it continues to be available in versions going forward. And what we're going to do is we're going to look at the 3 stages of what comprises an intelligent design run, what it is, what it isn't, where are some of the best places where someone might want to take advantage of this capability. I will do a brief demo in Vivado, really just to show how someone would go about using the intelligent design runs within the tool. And finally, we'll open up for some questions. Feel free to ask questions while I'm presenting. If I notice them in the chat, I'll try to address them right then and there. If I miss it, then we'll come back to it at the very end. So what intelligent design runs are is it's a new flow within Vivado to automatically incorporate machine learning techniques under the hood to try and meet difficult or challenging timing closure problems. This is based off of the report quality of results suggestions. So that's a feature that's already included in Vivado. It's a report that you can run on any design, and it goes over areas where you might want to look in your design for how you might be able to improve your design. It also incorporates a machine learning based strategy prediction. So this is a mechanism to tweak the tool. Obviously, when you run synthesis and implementation, there's quite a lot of settings that can be tweaked when running the tools. And in many cases, folks choose to use just the defaults. Here, using this strategy, it will take a look at your quality of results And from that, it'll determine if there could be some gains added by changing or adjusting those features slightly. This flow heavily relies on incremental compile. So many of you may have encountered if you're running a place and route, maybe it takes hours overnight. Incremental compile is a mechanism so that we can use the results from a previous run and just tweak our changes so that we could take advantage of already existing results to hopefully speed up the process of compilation, synthesis, and implementation. So as we can see from this graphic here, we start off with a design that is failing timing. And from that, the tool will first automatically look at your quality of result suggestion report, and it'll look at your timing constraints, your utilization, your clocking, your congestion. And from that, it'll determine if there are any techniques that can be automatically applied to try and meet timing. If it still is not able to meet timing, then there is this machine learning based strategy prediction. If that is also not able to meet timing, it will then do a design optimization technique similar to FizzOp design, but it has even more features that it would use to be able to try and meet timing. And hopefully, by the end of going through this process, your design will meet timing. Now, it's not a guarantee, but hopefully, especially if you have a design that's just very close but needs to get over the finish line, it'll help you get over the finish line. So like I said, it's a three-stage process. The first step is the design optimization. And I'm going to first go through what the three stages are at a high level, and then we'll take a look at under the hood, what does each step actually do inside of the tool. Then the next step is the tool option exploration. And then finally, the last step is the last mile timing closure. Now, we start off in stage one, but obviously, if at any step of the process, if we happen to meet timing, there's no reason to go any further. And so the tool will decide, okay, I was able to meet timing at stage one, and it'll stop the process. Likewise for stage two. Also, if you try to run intelligent design runs on a design that already passes timing, in that situation as well, it's just not going to run. There's no benefit by continuing to try and run this flow. Let's take a look at the design optimization. All right, so this process here, it takes advantage of the quality of result suggestions. All right, it's a mixture of machine learning based analysis and traditional flow charting and thresholding based analysis to determine what strategies might make sense to try and meet and improve on timing. So we're going to first take a look at our constraints file to see if there's any constraints that may cause us to not be able to successfully place and route a design. We'll next take a look at utilization. We'll be able to determine, can I, for example, better optimize my Boolean equations to better pack lookup tables, for example. Those types of techniques will be leveraged within this process to see if I can save on resources on a broader scale across the entire design. It also takes a look at your clocking, how clocking is established, the different relationships between clocks, to make sure that those are constrained properly. Because, for example, you could be failing timing because you haven't marked your clock domain crossings as false paths. And so that there will tell the tool, if I haven't put that constraint in, well, there must be a relationship between them, and the tool will try to meet timing to it when it's not actually possible, or it may not actually be realistic to your actual design. Then we'll look at congestion. This is obviously a larger problem. For example, if you have an RF SOC-based design with 8 channels of ADCs running at 500 megahertz, that can be a very challenging design to meet timing on. And so they will look at some techniques here, especially if we have large data widths, to try and improve on the congestion of that data moving across your device. And then finally, there's some timing checks that it'll perform to see if it can make some improvements. Now, I do want to note here, the intelligent design runs, this is not a quick solution. It is a time investment to perform this. And so AMD actually recommends that you build in the time it takes to do this upfront into your schedule. So they note here that it could take anywhere from 4 to 4.5 times to run this flow over your just traditional implementation. So for example, if you have a design that runs overnight, takes 8 hours, well, now you'll be looking at a design that could potentially take 32 hours in the worst case to actually finish this first step. So it is quite significant. So you should keep that in mind if you're going to approach the solution, what you may encounter and how you need to plan your schedule to account for this. So the next step here is the tool option exploration. So here it uses machine learning strategies to predict the best tool options to use. Now, if in stage one we're able to meet timing, then stage two is not even going to run. Uh, if, for example, entering into this stage, if our worst negative slack is greater than 50 picoseconds and our worst hold slack is greater than 0, this stage can be skipped and we can go right to stage 3. Now, the last mile time enclosure, that leverages the post-root FizzOp design and incremental compile to be able to iteratively try to run FizzOp design and meet timing at the last mile. Though to typically enter this stage, your worst negative slack needs to be no more than negative 250 picoseconds. So FizzOp design is not a solution. If you have a design that's failing by 1.5 nanoseconds, for example. Uh, that is something where FizzOp design is not able to correct for that. Um, FizzOp design really works well on designs where you have a few failing paths that are just very difficult. You don't have an option to maybe pipeline or maneuver things around, and you're just very close to meeting timing, but you just don't quite get there. And that's where you'd want to best take advantage of this capability. So it is possible to run an intelligent design run where because you're outside of this criteria, it will actually just skip it and say intelligent design run is not a candidate for this design. Let's take a look at the 3 stages a little bit now, more under the hood. So I had already mentioned the first step of running the design optimization stage is to start with a synthesis checkpoint. From that synthesis checkpoint, it's going to first look at your XDC file, your constraints, and determine if there is an implementation error or timing issue that would be impossible for the tool to fix automatically. So if that were the case, the intelligent design runs would just exit out at this point and say we cannot run a intelligent design run for this particular situation. So this might be if you have multi-cycle paths that are incomplete or places where you might have partial timing information applied. uh, Typically a good way that I would personally look to see if this would be a situation is you can look at the check timing report, and that'll tell you the places to look as well as the methodology guide for a methodology report for where there might be constraint issues to resolve before running intelligent design runs. The next step would be to run this cleanup utilization. So here it'll take a look at suggestions that will reduce utilization, but without having any penalty to timing. So it'll try to find equivalent solutions that use slightly less resources and then do not really have an effect or change to the overall timing of the design. After that, it'll clean up the clocking. So here it will run a place design to get an accurate clock skew timing number. And then if there are suggestions available with respect to your clocks, it will reset the run and then go through route design with those suggestions applied. So it will first have a cleaned up design, get a baseline, and then from that baseline, it will run an incremental compile to try a different technique with the suggestions to see if this improves on your timing. Moving into step 4, here we're taking a look at cleaning up the congestion. So in this step, these are suggestions that are applied after post route, And so if they do exist, it'll use the post route suggestions for things relating to congestion. If for some reason, if post route doesn't exist, it will run the apply those settings over to the post placement, though it would work better with the post route. And then finally, as a final step, it will clean up timing. It'll look at the individual failing timing paths and try to apply suggestions from the report as best as possible. So at the end of stage one, all post route checkpoints are then compared. So this will run multiple places and routes. And from it, it will look at the one that has the best result. And so this is why this can take up to 4 times longer than your regular implementation. And so based on those results, it'll either take the best run and move to stage two, or if it meets the threshold to go to stage three, it'll go right to stage three. So in the tool option exploration stage in stage two, the goal here is to obtain the maximum quality of result from the tool options. So here it will take it'll come up with 3 machine learning based strategies by looking at your current design, predicting which strategies might have the best impact to the design. And that can be different implementation settings, for example, and then from it, it will run those 3 designs. It'll compare the post route timing of those 3 results. And from that best run, if it passes timing, it'll exit. If it still doesn't pass timing, it'll then move to stage three. Now, because it's only doing 3 implementations at this stage, they typically will run in parallel. And so the time to go through this stage will be equivalent to a single implementation run. I do have a question here. Is the machine learning process local or does it require going to the cloud? Fantastic question. This is all local within the tool. I also, just looking back at a few other questions here, there was a question, is the IDR flow available for 7 series devices or just the newer families? Fantastic question. I believe I may be coming up to that on an upcoming slide, but just to answer that question, it is not available for 7 series. It is only available for UltraScale, UltraScale Plus, and Versal devices, but only in Versal devices that are not stack silicon based. But it does work broadly across UltraScale and UltraScale Plus. Let's see. Another great question here. Can you only check optimize XDC files, utilization, clocking networks through IDR, or is there an existing DRC you can run separately? Fantastic question. You can go through Vivado, and within Vivado, you can run a report utilization, report clocking, check timing. These are all reports that for many of the stages do run automatically. The only difference with IDR is that IDR is taking the results from report QOR suggestion and it is applying it to your design. So you can always look at those reports manually, though this is an automated process for taking advantage of the QOR suggestion and applying it to the design. And finally, one last question on this section. Is there a minimum system requirement for the PC running stage 2 to make sure 3 parallel runs properly? This is all handled through the design runs manager within Vivado. So another important point here, IDR is only available in project mode. You cannot do this in a non-project mode project. And the when you do a run, you specify the number of threads available to the tool to be able to take advantage of this. So if, for example, your machine only has 2 threads available and it's going to run 3, it will run 2 of them first, and then the third one will have to run after. So it will take, 1.5 Well, basically the time of 2 runs to be able to complete that. Now, moving on to the last mile timing closure of stage 3. So here, this is specifically for the cases where you're very close to meeting timing. This highly leverages phys-op design, and phys-op design works best when you're a couple hundred picoseconds or less. Really, even say you're failing by 50 picoseconds or less. That's the best candidate for running in this last mile timing closure. And so here, this will only run as a single run. So it will take the best result from stage 1, which gets passed to stage 2. And then in stage 3, it will run once and it will determine if timing is closed at this point. There are a few other questions here, and I'm going to just pause on them for a moment. I'm going to continue going through how you use it in the tool, and then I'll be able to address them afterwards. So when it comes to using intelligent design runs, it's very straightforward within Vivado, because this is only available within the Vivado in project mode. If you go to the runs manager, and I will be showing this shortly as well. If you go to the runs manager and if you right click on your implementation run, you only select close timing using intelligent design runs, and that will open up a second window that is specifically for managing these intelligent design runs. As we can see from the slide, the average gain on the UltraScale Plus designs are typically anywhere from 13% or better, whereas the Versal ones are 8% or better. So like I said, when you're very close to meeting timing, uh, this is a good candidate for this. It's also worth sharing. It's not great to use IDR for a very small design. The runtime for this could take approximately 4 to 4.5 times longer than a regular implementation run. For those situations, that's where you'd likely want to use phys-op design, for example, or maybe there's a methodology problem within the design that might need to be looked at. But really, the best types of designs for using this IDR flow is if you have very high utilization, very high congestion, places where you've tried everything you could think of to try and meet timing, and this is the heaviest hammer you could throw at it to try and get a design to meet timing. It's also worth mentioning, when it comes to intelligent design runs, you should always do your regular synthesis and implementation runs first. You shouldn't just jump right to intelligent design runs. You should see if your baseline design passes timing. And then if you're still having issues, that's when you want to come back and do intelligent design runs afterwards. So like I had mentioned, the Intelligent Design Runs tab opens after you select the closed timing with Intelligent Design Runs. And here you could see each of the stages, what's happening at each of the stages, the results of those stages. You can also tell the tool to launch the runs. You can, if you want to, you can examine a particular run. So you can open up the tool, the implemented design, to specifically look at a run to try and get a gauge of what did the tool actually do to get those numbers. So it's a very straightforward mechanism for that. There was one question on here about, how do I actually take my IDR result and, apply it to my design? And that is what this last item is here, this generate single pass implementation run. So if I run IDR and I get a result that passes timing, if I run the generate single pass implementation run, this gives a series of constraints that can be applied to your design so that it would be as if you just ran the flow that was the one that made you pass timing. And then you can reuse that for your design to continue getting consistent results. Just a quick overview here of items in the design runs tab. I did cover many of these already. The first one here is the properties. So these are different options for actually running the design. Delete will delete your run. You can only have one run at a time at any given time. Launch runs tells the run manager to kick off your implementation results. You can reset and start all over again. You can view the reports. You can open up the directory where the files are located. You can open up the design. And then, like I mentioned, the generate single pass implementation run that will set up the QR suggestion and give you a file that can be applied so that you can achieve the same results. This other view here is the Intelligent Design Run report. So this run report gives you access to all of the reports that get generated for each of the steps. So for example, in the cleanup XDC, there's a post running op design XDC utilization report that gets generated. A lot of other reports here. You have the ability to open up and look at everything that the Intelligent Design runs did during this flow. Also, while it's running, because obviously if this is going to take a lot longer, you would want to know how long is it going to take or how far in the process are you? Because, for example, 8-hour runtime, 32 hours to finish, you probably want to know where it is in that process. So here you can see a collection of the steps that have been completed and the areas marked with the circle here to show these are the steps that are currently running. So that is all I have with respect to what is IDR and how it all works. I am going to go through here before we switch over to the walkthrough and cover some more of the questions here. So I do have a question here on can you do load distribution of the parallel run if you have the Slurm or LSF from IBM, if you have those types of systems. If you already have your run manager configured to do those types of runs, because it's based off the run manager, you can apply those settings to IDR and it'll follow that. So you can send it to an LSF server, for example. Let's see here. After IDR flow, can I have the correct settings and strategies for the next design runs? So in that particular example, if I understand your question correctly, this is where you would do the generate single pass implementation run, and then those could be applied to your design so that it will continue to pass successfully. Once the stages are complete, can they be easily converted to non-project mode runs for future builds? And they can. The output result from the generate single pass implementation run, that is what's being applied to the design to run your implementation going forward. And so the only limitation to running IDR in non-project mode is because non-project mode doesn't have the runs manager. So if you pre-do all of your work with the runs manager, and then you get a set of settings that you're going to move forward with going on, you can just apply that in the non-project mode because at that point you're no longer running IDR. You're just, running your design through to implementation. I have another question here. Do you know if Xilinx AMD plans on adding support for the stacked silicon devices? They use large Kintex UltraScale and Vertex UltraScale Plus devices. So to answer that question, for UltraScale and UltraScale Plus, IDR is supported for all of those devices. The only place where it's not supported is for the stacked silicon Versal devices. So it works with the non-stack silicon Versal devices as well as the UltraScale and UltraScale Plus families across the board. Let's see here. If you manage to close timing with IDR, how can you make sure that your CI/CD service, so that's something that you would use to automate testing, for example, using GitLab or other places, will be able to replicate that. So if I understand your question correctly, my interpretation is that by applying the single pass implementation run, if you apply that to your design, you can include that as part of your flow in CI/CD to be able to replicate it. There is another question here on will the tool also keep track of the XDC files that it modifies per design run. Um, my understanding of how IDR works is that it's not actually applying the change to your XDCs. It is applying to the change to the constraints stored in memory. And so at the very end, when you generate that single pass implementation run, that will give you the checkpoints that include those constraints. You could also look at the reports to see what constraints were modified and work them backwards into your original design if desired. Very good question here on after using the generate single pass implementation run, if the code is changed slightly, like for example, adding one more register to the register map of an IP, what are the chances that the full IDR process needs to be rerun? So in that particular situation, I would have to say you likely do not need to run an entire IDR all over again. And the reason for that is one, you can leverage incremental compile. Additionally, if there's any methodology issues that have already previously been resolved, there in your particular example here, adding one more register that likely doesn't involve where those methodology issues might have been. So if you're applying the single pass implementation along with incremental compile, it's probably very likely that you won't have to rerun IDR. Uh, And then I'm getting quite a lot of questions here. They're great questions. So how fragile is the single pass file relative to the state of the design? For instance, if I were to change a few lines of code in one file somewhere, should the single pass be expected to still be pretty close to the same, or does it need to be thrown out and rebuilt from scratch using IDR? So that's kind of a hard question to answer. The reality is the file that's generated, it's likely looking at particular areas of your design where there might be issues. You can yourself look at the report quality of results suggestions, and so you may even want to go in and make those fixes yourself before using IDR to make those fixes. So it's likely that something tiny with respect to the entire design, that it's probably not that fragile in those cases. Um, but if the block that you make a modification to happens to be a source of high congestion or high frequency and things like that, it could likely affect your design. So if it's an area of the design that's very simple, straightforward, and not likely contributing to why you're failing timing, you're probably safe. But if it is that area of your design that is very complex and causing the timing failures, you may end up having to rerun IDR. But honestly, it'll be a case by case basis. I don't think I could speak to all those instances. Another question here on if the power to your, this is a great question. If the power to your PC goes out and interrupts the IDR run, are the checkpoints stored so it can be resumed without a full restart? Um, so I would believe likely in this case that because all the checkpoint files are stored, you likely will be you'll lose the current run that was running, but all of the checkpoint files that were stored previously should all be there, and the tool should be able to recover. All right. I'm going to now move on. There are a few other questions coming in here. I'm going to move on to the review within Vivado, and then we'll come back to some of these remaining questions here. All right, so I just wanted to be able to show how IDR works. Now, remember, like I said, IDR can take 4.5 times of your regular implementation to show that it works, to test out timing. So we're not going to sit here for 4 hours to have a really complex design and be able to show what the results look like. That being said, I do want to show an example of it working or of it doing its process so that we could take a look at the reports that get generated and help you feel more comfortable with what the environment will look like when you apply it to your design. So I'm working with here, Xilinx provides a host of example projects. There's a very old example project that comes with Vivado called the BFT. It's a series of parallel FIFOs that get fed into FFTs, go into another FIFO, and then a multiplexer to select what's the actual output that you want. So this is a small project, has some logic in it. And the reason why I'm mentioning this is because if you want to try this yourself, you can create a project with this BFT example design. We don't need to provide the source code to you. You can get to this directly. So what I have here is that BFT project, but I've already run synthesis on it. I've already run implementation. And you can see from the design runs, one, if I go to right click on the implementation, the first thing I notice here is that the close timing using intelligent design runs is grayed out. And the reason for that is because you can only run it once. You cannot, keep telling it to run intelligent design runs. And because this design I already ran it on, it is grayed out. But if I had not already run it, I would select that there, and then that would open up my intelligent design runs tab. One of the reasons why we can see that our design is a candidate for intelligent design runs is that if we look under methodology, it's reporting that there's 4 critical warnings and 69 warnings. So I can go under my implementation and I can select report methodology. I already have that open here. And we could see that in this particular design, there is a critical warning between 2 clocks in the design. And the reason for this is because I have my BFT clock and my WB clock. And based on my constraints file, they are just listed. One of them is running at 100 megahertz, the other one's running at 200 megahertz. There is no other constraint in my design that establishes whether or not these are asynchronous to each other. So because of that, Vivado just assumes these are synchronous clocks. So it is saying, hey, these clocks are related because you haven't told me otherwise that they're not. So it's going to try and time them, even though they're likely not related and go through clock domain crossings and things like that. So this would be considered what they're calling just a bad practice, that really you should put a asynchronous clock group constraint in there or a false path constraint so that it would then, this warning would go away. So if we take a look at the intelligent design runs, this is just the run manager for the intelligent design runs. We can see that it actually only ran stage 1. And the reason why it only ran stage 1 is because taking a look at the device view, this design is actually fairly tiny for the Kintex UltraScale part that it's on. So it's not a challenging design to meet timing with. It's very straightforward. So here it's just showing me that it ran stage 1. And in that stage 1, we can see, I just want to make sure there's enough room here. We can see that it ran the cleanup XDC, and then it ran the first pass results across all of them. And by the time it came out of here, it passed timing, so it didn't need to go to the future stages. We can also take a look at the flow statistics. And so here we can see the various reports that came out as a result of that. We can also look at the quality of result assessment score. So here, the higher the number, the better. So if we had, for example, zeros or ones, that would mean, hey, that's serious problem that you need to update in your design. But here we have 4s and 5s, which means there really isn't much wrong here. There's just might be some things that you want to look at. So here it's looking at the different congestion levels, the worst negative slack, and it didn't move to the following sections because we have, positive, negative slack, very good numbers here. We meet timing by a mile. But I just wanted to show this as an example for when you want to run it on your design, all you have to do is go to design runs, turn on intelligent design runs, and then under this tab, select launch runs and let it go and wait for your results. Mhm. So really, that was all that I was planning to go over with everyone today. I will take the next minutes or so to be able to go through some of the questions here. I do have a lot of questions still outstanding. Um, with respect to what folks might want to do with this going forward, I'd highly recommend we have a whole series of courses, the Designing FPGAs for the Vivado Design Suite from series 1 through 4. And that's a really good candidate to get to know how to use the tool, where all the various reports are, all the different features available within Vivado and meeting time enclosure. And so that's definitely a place where I think folks would benefit the most from with this type of thing. This is a topic that comes directly out of one of those courses. And so if you found this interesting, you should definitely reach out to us if you're interested in taking those courses.
Yeah, if you are interested, I dropped the link for the first of the 4 of our FPGA classes into the chat panel for you. You can use that to follow the website along to the other classes, the 2, 3, and 4. So if you want to check them out, that is now in the chat panel for you.
So now looking through some of the questions here, there's another question on if the 7 series devices are available. Unfortunately, this isn't available for 7 series. Another one on does IDR incorporate any option explorations or optimizations for the synthesis stage? It does not. Everything that it does is in the place and the route area. So it does not do synthesis. Uh, Follow-on question here for is there any limitation regarding the DFX flow? Um, I don't have a clear answer to that right this moment. I would need to check with someone to make sure. So that is something we can get back to you on. Another question, does the single pass implementation run depend on incremental compile? So each stage is based on incremental compile. So for example, within stage 1, it'll use well, it starts with just the synthesis results. It'll get the post place results, and then some of the other stages will use an incremental post route approach. Does someone need to run a standard implementation without using any Vivado optimizations before using IDR? So as something I had mentioned previously, the general recommendation, technically nothing stops you from going into design and saying, hey, run IDR. Though generally, that's not really how IDR is meant to be used. Uh, Typically, when someone wants to use IDR, they should have already implemented their design, recognize that timing has failed, that they are not able to correct it for their own reasons because, complicated design, for example, and that's when you want to run IDR. So you typically want to at least baseline your design first, and then following baselining, if you're still not meeting timing, this is when you would want to bring IDR in. I have a question asking if I could share slide number 10. And here is slide 10 with all of the notes applied. And you will all get the recording for this as well. Great question here on does this design work with both HLS and HDL coded designs? And yes, it does. The when you take your HLS IP and incorporate it into your Vivado design and you're running the tools, it will apply these techniques to your HLS IP as well. Another follow-up question here, is the output of the single pass implementation run Vivado version dependent? So if 6 months from now, the Vivado version is uh, revised for the project, would it still be compatible? That's a difficult question to answer. There's a few different variations for how someone might want to answer this. For example, if you increase the version of Vivado, you may have updates to your IP. that especially IP that were within Vivado. So if that were the case, you would need to rerun implementation to account for all that new IP. And so it is possible in that situation that you would have to rerun your IDR. My personal opinion, if you're going through the process of migrating to a new version of Vivado, it would likely make sense to rerun IDR if you need to, because there could have been improvements to Vivado that now make you meet timing anyways. But you will likely want to run IDR again to take advantage of all the new features and abilities in that latest version. Question here on, does Vivado take different clocks as related? I believe that other tools do exactly the opposite. So Vivado, every clock in your design, um, especially if there's a place in your design where there actually is a design interaction, where there's paths crossing between those domains, it assumes that they're related. And then you have to explicitly say that they're not related in order to time them appropriately. There is a question here on, is there an AMD document that you'd recommend as reference? And I believe, let me just quickly grab it. I believe that there is a particular version user guide that does mention intelligent design runs for implementation. And that would be the Vivado design methodology. That's user guide 949. And I will paste that in the chat to everyone. There's a question here on, are the tools that you mentioned at the beginning available for the 7 series? So this intelligent design run is not available for 7 series part. It does. Another question on, does it work on incremental compile? This is all based on incremental compile. Uh, can IDR runs be scripted with Tickle? And they can. Everything that you do within Vivado has a corresponding Tickle command. So if you are running a scripted project mode flow, you can extract those commands. Let's look at the journal file here. And you can run those commands. I don't have it in this particular one because I had reopened it. But if I took a look at my old one, I'd be able to find those exact commands. There's someone that was attempting to do the BFT project on their own computer. In order to do the intelligent design runs, you have to make sure that you select on that BFT project the UltraScale Plus, or sorry, the UltraScale device. It's the XCKU 035. If you selected the 7 series, you're not going to have the option for intelligent design runs. And then just one final question here. Can I elaborate on the ML strategy settings in stage 2 versus different setting runs that are applied in stage 1? And my understanding of how the tool works is that it is looking at the implementation based on the settings. So when you go into settings and you look at implementation, there are a list of different strategies available. So there's all these different strategies. And it is selecting 3 of these strategies that might make the most sense for your design based on the results that you had in the prior stage. All right. So I appreciate everyone's time here today. I hope that this presentation was useful and that it helps you all with meeting timing on your designs. If meeting timing is something that you may have some issues with, by all means, please feel free to reach out to us. That's a conversation that we would be more than happy to have with you all. And I'll hand it over to Sharon.
Great. Ellie, I really appreciate you sharing all of your expertise with us today. I will send all of those links that were in the chat panel in an email to you along with the recording. The recording will take a couple of days. I'll probably get those links out to you sooner. The recording will be a YouTube link that I will send out since someone just asked that question. So you will get that in a few days once it's processed and it's ready. It does take a little while for me to get that done. So I will send it to you as soon as I have it. If you haven't already, do please check out our webinar series. We have a webinar every month. We also have a workshop, which is 4 hours every month. All of those are no cost to you. They are sponsored by AMD Xilinx. We are one of their partners, so we are providing this to you at no cost. So I hope you will join us for additional training opportunities. And if you're interested in some of our paid classes, the course calendar is also available for you to check out some of our deep dives, like the FPGA 1 through 4 classes that we have where you can learn more about this. So I appreciate all of you guys joining us today, and I look forward to seeing you back for some of our future events.
Bye, everyone. Take care.